What's up, everybody? Welcome to another video, and I hope you're ready to flex those brain muscles. I'm so sorry for my recent inactivity. As some of y'all know, I'm taking a summer differential equations class. So first of all, it's a summer class. It's very fast paced. We meet every day. But secondly, it's differential equations. It's a notoriously hard course. The material is not easy. It takes a lot of time, but I've been putting in that time, but that means I've had less time to make videos. So sorry about that. I'm back on track though. I am caught up. Today I took the second exam in the course, and I'm honestly really enjoying this material so far. I enjoy most of the material and I've been succeeding, but I have to say part of the reason for my success is because of two people. Black Pen, Red Pen, and Professor Leonard. Their videos on differential equations are so freaking good. It's changed the game for me. I'm killing this class because of these two people. So it's pretty cool. Make sure you check their channels out. I'm sure you already know about them, though. They're two of the biggest math YouTubers around right now. But I just want to make it clear that I still use YouTube as a resource. It's an amazing resource, and I think that's so freaking cool that you can search anything, and you can learn anything you want for free, right? That is so freaking cool. And I've been doing this since pre-cal. Since I was in pre-calculus 3 years ago, I've been using YouTube as a resource to supplement the classes I'm taking, because it's very rare that I leave a math lecture and I'm like, yeah, I understand all this stuff, easy peasy, right? Usually I have quite a few questions, misconceptions, that sort of thing. So I go to YouTube and I search these topics, and I'm able to clear up those questions. I'm able to gain the understanding I need to succeed in the course. And that's part of the motivation for me to make these videos. And it was part of the motivation for me to create this channel. It's like, all right, now that I know enough math, I feel like I can contribute. And again, I'm not as mathematically advanced as most of these other math YouTubers, but I'm still at the point where I can contribute, I can, give back, sort of. That's sort of how I think of it. Because again, a lot of these math YouTubers have impacted me and helped me succeed so much throughout my undergraduate math career, right? So I hope one day, or if not already, I can impact someone else in the same way they've impacted me. And I hope one day someone will finish a course and get an A and look back and say, man, I'm so glad I watched Mr. Tucci's videos from Brain Gainz, because if I wouldn't have done that, I wouldn't have done as well in this course as I did, right? So I hope one day people can say that. The thought of that is so freaking cool. It excites me. It motivates me to make videos like this. So sorry to get all sentimental on here for the intro, but I had to get that out of the way. Really, I'm one of y'all. If you're here to gain knowledge and understanding, I'm off on other channels doing the same thing, maybe just at a different level. You know what I mean? But at the end of the day, we all have a common goal: to grow, to learn, and to flex our brain muscles, and that is so freaking awesome. So thank you for watching. I am very proud to be part of this community, and for y'all today, I have an intro to differential equations. And maybe you're thinking, wait a minute, I thought you were taking this class. It's true, I am, but you know what they say: if you want to really learn something as deep as you possibly can, if you want to even master a subject, go teach it. Try to go teach it. Challenge yourself to see if you can do it, because first of all, you may realize you don't know the subject as well as you thought you did, but second of all, and more importantly, you will learn so much along the way. Just about every video I've made, even the algebra videos, I learned something. Whether it's looking at something a different way or making a connection that I hadn't made before, I learned something. And you can ask any teacher and they will tell you, I guarantee they'll tell you a similar experience. They're like, yeah, I'm constantly like making new connections, having new understandings just through teaching, right? You do learn along the way. So a good suggestion, if you really think you have a subject mastered, go try to teach it. Try to make a video like this, maybe, who knows? But we're gonna do an intro to differential equations, and I think this video will be really good for someone who maybe is taking differential equations in the future and wants to know what to expect, or just for anyone in general who wants to, look at some beginner intro level differential equations and look at what the deal is with these equations. So hope y'all enjoyed this video. If you do, as always, make sure you're subscribed, hit the like button, share this with whoever you think may enjoy or benefit from it. Let's go ahead and get into it. This is a differential equation. And in general, a differential equation is just an equation that relates a function to its derivative or derivatives, right? So in this case, we have a function y, and this is a function of t, as we can see. And we see t, it's kind of like our x, it's our independent variable, but we see t a lot instead of x in differential equations. So just warning you, don't be scared of the t. But I think part of the reason why is because differential equations can be used to model things, specifically things in the physical science realm, like physics, and a lot of these models have to do with time, something changing with respect to time, so we use t. That's my best guess for why we use t, but don't be scared of it, all right? Don't be scared of the t, it's just like x. So we have this function y, and it's equal to its first derivative. This is a differential equation, and really this would be a first order linear differential equation, but we'll get into classifying them later. So can we think of a function, maybe? Can we think of a function where we take the derivative and it equals the function itself? I'll give you about 5 seconds to think about it. All right, if you thought of e to the t, you were correct. Or maybe you thought of e to the x, but we're doing t right now. So e to the t. So let's go and write this out and let's see what this means. Y equals e to the t. So what exactly does this mean? Well, this is a function y, such that when I substitute in e to the t in for y, and when I take the derivative and substitute that in for dy dt, I get an equation that is true. So we say that this equation satisfies this differential equation. What does this mean? Well, that means this equation is a solution to this differential equation. Isn't that pretty cool? When we deal with equations in algebra, we always get like x equals 12, x equals square root of 3, right? We get a real number as our solution. But in differential equations, our solution is actually an equation. Pretty cool, right? So this is our solution, and I'll put a formal theorem up. It's something like an equation is a solution to a differential equation if and only if the equation satisfies the differential equation. So we use the term satisfies, but again, that just means that when we do the necessary substitutions, we get an equation that is true. It works out, right? So in this case, e to the t equals e to the t. Clearly that's true for all values of t. Therefore, this equation satisfies this differential equation. Therefore, this equation is a solution to this differential equation. Following? Okay, good. Can we think of maybe another solution? Can we think of another equation that satisfies this differential equation? So another function where when you take the derivative, it equals the function itself. I'll give you a few seconds. All right, so what if we just add maybe a 2 out in front of here? What if I just write y equals 2 times e to the t? Now, let's do the necessary substitution. So in other words, 2 times e to the t, substitute that in for y. Then let's take the derivative and substitute that in. So what do we have? The derivative of e to the t is just e to the t. And the 2 is just a constant. It just chills out in front. So we have 2 times e to the t equals 2 times e to the t. We found another solution to this differential equation, right? And maybe you already see what's going to happen from here, but I can pick any real number and stick it here, and it will be a solution to this differential equation. So not only is our solution an equation, but we have infinitely many solutions. Pretty cool, right? So how can we maybe represent these infinitely many solutions with one equation? Well, we can write y equals c e to the t. And c is just any constant. That's why we use the letter c. It's just a constant, a real number. And this is an equation that represents all our possible solutions, all the infinitely many solutions to this differential equation. And this equation actually has a special name. We call this the general solution of this differential equation. This is the general solution, and that is because it represents the infinitely many solutions. So we always have at least one c. Sometimes we'll have c1, c2, etc. Because again, it's infinitely many. So we have an arbitrary constant or constants if there's multiple involved. So what can we say about this? Well, this is a general solution, and a lot of times we call this a family of solutions. You may hear that term thrown around. But what we'll do later in this course, and really not that much later, I guess like 1 or 2 weeks from this, is we will solve for this c. So we'll be given conditions that we need to meet, and we use those conditions to solve for c, and then what we end up with is what we call a particular solution to the differential equation. So just keep that in mind moving forward. For now, we're just going to focus on these general solutions, but in the future you will do initial value problems. It's a huge part of differential equations, and that's when you'll end up with a particular solution. So instead of c, you'll have a real number there, and you'll have one single solution of these infinitely many, of this family of solutions. You'll have one of them. So hopefully this is clear, hopefully this makes sense. We have a differential equation. It relates a function to its derivatives. An equation is a solution to a differential equation if and only if the equation satisfies the differential equation. And when we have a solution, really what we have is infinitely many solutions. Depending on the equation, we can write the solution using an arbitrary constant or arbitrary constants if there's more than one. and we can represent those infinitely many solutions with an equation that we call the general solution. So hopefully this is clear. Hopefully this makes sense. All right, guys, so here we have our first example. We are going to verify that y equals sine t is a solution of y double prime equals negative y. So this is a very common kind of problem to see in the very beginning of an undergraduate level differential equations course, is these verifying an equation as a solution kind of problems. But really it's pretty straightforward. We just need to know what it means for an equation to be a solution of a differential equation. We already know that, right? And we need to know how to check. We need to know how to take the derivative of this function and the second derivative and that sort of thing, and know how to do the necessary substitutions and not make any algebra mistakes. So if you know how to take derivatives and if you know algebra, you can solve any of these problems. You can verify that any equation is a solution of any differential equation. But we will do some examples. I just want to make it clear that it's not that scary, okay? So y equals sine t. I like to write out what I'm trying to verify, and then I like to write out everything I need to make those necessary substitutions. So I don't need y prime, but I need y double prime. So it makes sense to go in order. I will find y prime, because I can just take the derivative of that to get to y double prime. And maybe you don't need to do that with this kind of simpler example, but as these get more complicated, it's really smart to do that, to find each derivative, go in order. Don't try to skip any, because you're prone to making mistakes there. So derivative of sine t is cosine t, derivative of cosine t is negative sine t, and maybe you can already see that this is going to indeed satisfy the differential equation, but we'll do the substitutions. We have y prime, and that equals negative sine t, so we have negative sine t, and this equals what? Negative y, so we have a negative chilling out in front of this y. Y equals sine t, so we just have negative sine t, and we can quickly see that this is indeed true. Therefore, this equation satisfies this differential equation. Therefore, it is a solution. We have verified it. We are done. But we can go a little bit further. Let's look at one more thing, because it is kind of cool to see what do we think the general solution of this differential equation is. What do we think? I think it's a similar situation as we had in that last example, e to the t, just this time with sine, right? Because think about it. Any real number that's out in front of this sign, as we continue to take derivatives, it's just going to chill out in front, right? So a general solution would actually be y equals c sine t. And the cool thing about this example is there's actually another general solution. We have two different families of infinitely many solutions, which is pretty cool. You don't see that too often, but y equals c cosine t would work as well. And you could verify this, maybe do that on your own, verify that y equals cosine t is a solution of this differential equation. But it's pretty cool to notice that, you know, we can quickly find the general solution for these. And later in this course, we look at different methods of finding the general solution of differential equations, because as they get more complicated, you really can't just look at it and be like, oh, I think this is what's going to happen. You just can't. So we do learn some methods, integrating factors. We learn separable. We do separable differential equations, that sort of thing. But we'll continue with these verifying that an equation is a solution kind of problems. All right, guys, so at this point in the video, I encourage you to pause the video, try to do this on your own. Try to verify that y equals x squared is a solution of this differential equation, then press play to check your answer. So y equals x squared is what we're trying to verify is a solution. And what do we need to do our substitutions? We just need y and y prime. So I can simply just take the first derivative, which is just 2x, really easy power rule. And now I have everything I need already. This is going to be a quick verification, all right? Let's see. Y prime, I'm substituting in 2x for y prime. So x times 2x, that gives me 2x squared, equals, let's see, 2 times y equals x squared, 2x squared. This is always true. Therefore, we have verified that this equation is a solution of this differential equation. These are looking a little too easy. Let's see if we can step it up a notch. All right, guys, so we have stepped it up a notch, but I still encourage you to pause the video and try this on your own. Press play to check your answer, all right? So we're going to verify that y equals e to the 3t is a solution of this differential equation. So let's write out all the stuff we need off to the side. We have y. That's what we're trying to verify is indeed a solution. So really we just need y prime and y double prime. Because let's look at our differential equation. We have y prime, y double prime. So we need those three things to do all the necessary substitutions. So y prime, what's the derivative of e to the 3t? Well, it's just e to the 3t, right? but then we have to remember chain rule. Do not forget chain rule. So e to the 3t, and then we take the derivative of this exponent, which is 3. So we end up with 3 times e to the 3t, okay? And then what do we have next? We can see this pattern sort of continues. Each time we go to the next derivative, the only thing that changes is we multiply by 3, because the derivative of e to the 3t is 3e to the 3t. But now we have this 3 chilling out in front. Hopefully that makes sense. So we have 9e to the 3t. Bam! Now we have all the stuff we need. Let's see if we can do these substitutions and not make any silly algebra mistakes. So 9 times e to the 3t, that's going to go here for y double prime. 9 times e to the 3t minus 3 times y. So that's minus 3e to the 3t. And this equals what? 2 times y prime, which is 6e to the 3t. 6 times e to the 3t. All right, 9 times e to the 3t minus 3 times e to the 3t equals 6e to the 3t. Right? I can do 9 minus 3. They are like terms. So now I have 6 times e to the 3t equals 6 times e to the 3t. And it's pretty clear to see now that this is a true equation. Therefore, this equation satisfies this differential equation. Therefore, it is a solution of this differential equation. So hopefully that makes sense. Let's do one more example. All right, guys. So we stepped it up another notch. And here's our last example. And I encourage you still, pause the video, try it on your own, then press play if you get stuck or if you want to check your answer. So y equals x times e to the negative 2x. Verify that this is a solution of this differential equation. So we need y, y prime, and y double prime. We were given y, okay, x times e to the negative 2x. Let's go ahead and first find y prime. What do we have to do here? What rule is this? We have an x times e to the negative 2x. That is product rule. So think of this as our u, x is our u, and v is e to the negative 2x. And the way I think of it is u prime times v plus u times v prime. Or the way I really say it in my head is the derivative of the first times the second plus the derivative of the second times the first. That's what I kind of say in my head as I do this. So if you have a slightly alternate way of thinking of it or doing it, that's fine. Do whatever works. So derivative of the first is just 1 times the second. So I just have e to the negative 2x. Plus the derivative of the second, that negative 2 is going to pop out. I'm just going to erase this plus and make it a minus, right? That negative 2 is going to pop out. Minus 2x times e to the negative 2x. By the end of this class, you'll be so good at taking derivatives. Anything that has to do with e, you'll just be able to get right to it. All right, let's find y double prime. Can we do any kind of simplifying here, first of all? I think it would be good to just leave it like this. So y double prime, first let's do the derivative of this first term of y prime. That is simply just negative 2 times e to the negative 2x. And then we have to do the derivative of the second term, which actually uses another product rule. We have our u and v, and there's a couple different ways you can think of this. I like to group the constant together with the x and think of that whole thing as the u and this as the v. You could sort of think of the negative 2 being out in front. There's however you want to do it, all right? But I like to do this. Minus, and then do all the stuff I need here, and my u is 2x, and my v is e to the negative 2x. That's how I'm going to do it. So derivative of the first is just 2 times the second, so 2 times e to the negative 2x, plus the derivative of the second, which that negative is going to come out and multiply with the 2. So I actually have negative 4. Let me make sure that's right. Yes, that is right. Negative 4x times e to the negative 2x. And that's just the way I do it, because then once I remove these brackets, all I have to do is change that to a plus. So this is the way I do it. Maybe there's a better way. Let me know in the comments if you're like, dude, you're doing it the hard way. Then let me know. I'm open to, you know, whatever way is best. I guess there is no best way. Whatever way works for you is the best way, okay? So combine these. That's what I'm going to do at least. This equals negative 4e to the negative 2x. These are like terms. Plus 4 times x e to the negative 2x. All right, so now we need to do all our substitutions. I may need some more room for this. Let's see, because I have y double prime here, y prime, and y. Let me rearrange and make a little bit of room here. All right, guys, so I rearranged, made us a little bit of room here, and that's what happens at differential equations. I had a problem on the board the other day. It was a homework problem I was doing, and it literally took up a full row, and then overlapped into the second row because there were so many terms in it. So be prepared, be ready for that later on in this course. But let's go and do it. We can do our substitutions. We have everything we need. So let's see, y double prime, that's just negative 4e to the negative 2x plus 4x e to the negative 2x, all right? Then y prime is right here, so I'm going to copy down plus 4 times all of y prime, e to the negative 2x minus 2x e to the negative 2x, okay? And then what else do I have here? Plus 4 times what? X times e to the negative 2x. So I can just write that all together. And maybe you could have just gone straight into distributing. I wrote this out just to write out each step, but maybe you could have done that. That's fine. You can skip steps as long as you're confident that everything's legit. So this equals 0, or that's what we're trying to verify, that this is a true equation. So right off the bat, can I cancel anything? I don't think I can yet, but I'm going to distribute this 4 into here, and I'm going to end up with, let's see, negative 4 All right, and this is the most satisfying part of differential equations, when you get to equations like this and you get to pull out your red pen or marker and you get to do a bunch of canceling. So look what we have here. We have terms with x and e to the negative 2x, and then we have terms with just e to the negative 2x. So let's say we have 4x times e to the negative 2x, and then we have another one of those here. So together those make 8x e to the negative 2x. We have that subtracted here. Bam, bam, bam. Isn't it so satisfying? I love this part. And then we have plus and minus. Bam. Those are both gone. What are we left with? Anything? All gone. 0 equals 0. Pretty nice, right? We have verified that y equals x times e to the negative 2x is indeed a solution of this differential equation, and we did it using a red marker, and it was very satisfying. So I hope that made sense, and I hope you all enjoyed this video. If you do, make sure to hit like, make sure you're subscribed, leave any suggestions below for future video topics. I'm willing to make whatever. I'm excited for, to continue to do this. So thank you all for watching, and thank you all for the support you've given me, and keep flexing those brain muscles. See you all in the next video. Do the substitutions we need to do. So we have this y double prime is 9 times e to the 3t. So we're going to put that right here. 9 times e to the 3t minus 3 times y, which is 3 times e to the 3t. So that is actually just 9 times e to the 3t. That is 0. So hopefully this equals 0. 2 times, let's see, y, whoopsie.